I have two functions here. So the first is f of x, where y is 3x plus 1. Now, what if I were to say, can you find the gradient of each of these functions? What's the gradient? The gradient is rise over run, right? It's how much y changes when x changes a certain amount. So, I draw a right angle triangle here. Let's say y goes up 3, x goes up 1. So when x goes up 1, y goes up 3, then we write it in the form y equals mx plus c. The y-intercept is 1, so stick that on there. 3x y equals mx plus c. And we have found the gradient of this line. We've found how much y changes with respect to x, because if x changes 1, y changes 3. That's what this is saying. That's what, in the equation y equals mx plus c, this is what m describes. That's all it does. Now this works for straight lines, but what if we had this? We have a quadratic here now. What if I want to find the gradient of the quadratic? Well, graphically, if I want to do anything with this, say the gradient here, okay, is going to be very different to the gradient here, is going to be very different to the gradient here, is going to be very different to the gradient here. What does that mean? So the amount that y changes with x changes as x changes, which that sounds really, really complicated in theory, but once you simplify it a little bit, it becomes a lot easier to digest. So we might not be able to just find one value that describes the gradient of this, because the gradient is always changing. But what if we could find the gradient of this at some certain point? Well, the most general way of doing this, what if we could find the gradient of this function at a given x? Well, how would we do that? We could describe that as another function. So say I get out a dark blue here. Let's say I have another function called g prime of x. We're going to call this the derivative of g. And we call it the derivative because it's related to g by giving us the gradient of g at a certain point, right? Because both of these graphs, they still have gradients. Just the difference is f of x has a constant gradient. This never changes. It's always 3. This will always be 3. It's always a gradient of 3. But this, it has a gradient that changes. So let's find its gradient at certain points, okay? And you can have a bunch of straight lines representing these gradients. Let's find these. So in this case, and I won't get into the specifics of how you find this just yet, g prime of x, or the derivative of g, is 2x. And let's see if that's right. What does this mean? If I have at a certain x point, g's gradient will be 2x. It will be 2 times its x coordinate. So let's look at that. So at x equals 0, the derivative of g, or g prime, is 0. So its gradient is 0. Let's look at that. Yeah, this looks correct. This isn't moving any particular way. We've just got a line with slope 0, y equals 0x plus something. This is probably y equals 1 because it's got a y-intercept of 1 here. Then let's look at g prime of x is, maybe it's something, let's look at g prime of x when x is 2. Let's look at the derivative of g when x is 2. Well, it's going to be 2 times 2, it's going to be 4, so maybe something looking more like this, and there you go. It looks exactly like that. Maybe g prime of -2, that's going to be 2 times -2. So it's going to have a gradient of -4, so let's look at that. And as you can see, it always touches the line at one specific point, and at that point it describes the gradient of that specific point on the line. And we can get a bunch of these for every single point on the line. And this is the idea of differential calculus. This is what a derivative is. All it does is give you the gradient of a function at a certain point. It will give you how much y is changing for every change in x at a certain point. So here 2x means that at x equals 0, if I have x, I can make a table out of this, g and its derivative and x. At x equals 0, g will evaluate to just 1. G prime of x evaluates to 0, because look at this. Even if I look at a line like this, even if I changed x by 1,000, y wouldn't change one bit. So g prime is 0. Let's say at x equals 2, g is going to be 5. Okay, 2 squared plus 1 is 5. And then g prime is going to be 2 times x, so g prime is going to be 4, something like this. This is what that gradient looks like at x equals 2. And that does seem fairly accurate. I can draw a bunch of these, but whatever. So g prime being 4 tells us that whenever x increases by 1, y will increase by 4 in response, where y is given by g of x. So differential calculus, key concept to remember, just know the derivative of a function gives its gradient at a certain point, okay? When you have a derivative, that is just a function related to another function, and it gives the original function's gradient at any point when you put x in there. One alternative way of writing derivatives, which I might as well go over, you don't have to put this apostrophe here, you don't have to call it g prime or simply the derivative of g. The more particular way of writing it is dg over dy, okay? No, dg over dx, I mean. Because here, g is the variable that we're observing the change of, and x is the variable that g is dependent on, okay? G is the dependent variable, and x is the independent variable. We're finding the rate at which g changes with respect to x at any given x. And this here is called specifically Leibniz notation, invented by Gottfried Leibniz, who co-invented calculus with Isaac Newton, who I will not go on a tangent about. Yeah, okay. I deserve to die for making that joke. I know nobody got it tangent, because this gives you the derivative of a function, gives you the slope of the tangent line at any given point. Because the tangent line to a function it's simply just a line that touches it at one specific point, at that point, and describes the gradient at that point. But do not overcomplicate it for now, just remember. Here we have Leibniz notation, dg over dx, the derivative of g with respect to x is 2x, and here we have, I think this is called Lagrange's notation, somebody will correct me, g prime of x equals 2x. They're very similar. You can just call this the derivative of g, or again the derivative of g with respect to x, but the point is that it's a function that describes the gradient of g at any given x.